All right, let's look at chapter 12, and we're going to look at kinetics. Kinetics is a study of how fast. Now, how fast a reaction goes is incredibly important. Reaction goes too fast and you're doing it in industry, you might have explosions. If a reaction is going too slowly, it might be impossible to do. So we're going to have to look at how fast reactions go and what will affect their speed. So we're going to start out with chemical kinetics, how fast a reaction will go. Now, in order to consider how fast, we're going to have to define the term rate. And we're going to begin this study with a rate. And a rate is like a speed. We know a speed, if you're driving, is a change in distance over the change in time. If you drive 35 miles an hour, that tells you that you will cover a distance of 35 miles in 1 hour. Our rate is going to be the same. We're going to look at a change in concentration over a change in time. Now, there's a number of things that can determine the rate. They include concentration. If you've got more of the reactants, our reactants are going to be able to get together faster for the reaction to occur, and we're going to look at an increased rate. We're going to define the definition or define concentration dependence in terms of an equation called the rate law, and we're going to write those. Time dependence. Time dependence says that if you've got a reaction going and over time the concentrations of the reactants are going to go down, that's going to tell us that the rate is also going to go down, and we're going to determine something called the integrated rate law. And these are the equations that are going to tell us how long or how much is left. And then we're going to look at temperature. We know that if we want to slow down a reaction, we're going to cool it down. If you want to slow down how fast food decomposes, put it in the freezer. It gets nice and cold. The temperature dependence is going to be described in the Arrhenius equation. And then we are going to talk about the theory behind chemical kinetics and do problems on these concepts. And we've seen this. We know that if we put a nice lizard out in the sun, and as the body warms up, the reactions that take place in the lizard's metabolism are also going to speed up. Surface area can change how much of the concentration or how much of the reactant is available to react. So if we take and we put an iron powder versus an iron nail into some hydrochloric acid, the powder is going to react much faster because a lot more of it is available to react. The solid here with an iron nail is going to be much slower as much less of the iron is available to react. Concentration. If we have a statue, and most statues are made from marble, or marble are carbonate compounds, and they're going to weather over time just because of rain and freezing and expansion and contraction of the water. And we know what's going to happen. We know they're going to decompose. But if instead we have pollutants and we have sulfur dioxide actually reacts with water and it's going to make an acid. And when we make an acid out of that, it's going to react much faster. So therefore, we increase the things or the concentration of things that we have that can react, in this case an acid, and the reaction will occur more quickly. This is a visual illustration of the decomposition of hydrogen peroxide. The color is just our way of looking at it because it sometimes can be very hard to see kinetics. It can be very difficult also to measure how much stuff reacts, but we can take and find its concentration over a period of time, and this is going to tell us how fast something is going to react. The reaction or the rate of the reaction is going to be the change in concentration over the change in time. So let's look at the numbers. Again, we've got peroxide reacting. If we start out with 1 molar at time 0, and at 6 hours, we have half of it left. And then we go another 6 hours, and its concentration goes from 0.5 to 0.25. We also are decreasing in it, but it's not the same amount. If we go 6 hours more, we go from 0.25 to 0.125, and the amount that goes away is getting less for each of these 6-hour periods. And we can look at the rate of decomposition, where the rate, by definition, is going to equal change, our delta, here this is a delta, is change. And our change tends to be final minus initial. Because we're going to have less at the end than we start with, our rate here is going to be negative. It's going to go down. And we're going to look at change in concentration of the peroxide over the change in time. Very few things have a constant rate. Almost all reactions, as the concentration goes down, the rate is also going to go down. And we can see this in the different rates. These are going to be average rates over those time periods. If we graphed it, it would look like this. When we draw a tangent, which is a line, a straight line that fits at a certain point. So if we draw a tangent to this, it's going to be an instantaneous rate at that particular time. But in general, those are very hard to measure. And what we measure in general instead is an average rate where we take two of these points and we take the concentration and the time between them and we get an average rate. So unless you graph it out and draw a tangent line, you're going to find an average rate, not an instantaneous rate. Now the rate depends on whether or not we're looking at the reactants of the product. So this reaction here is 2 ammonia. It's going to break apart and make 3 nitrogens and, 1 nitrogen and 3 hydrogens. Ignore that typo. 2 ammonias going into 3 hydrogens. Now, what does this tell us? The relationship between the ammonia and the nitrogen. 2 ammonias react for every 1 nitrogen. So the rate for the ammonia is going to be twice as fast as nitrogen. Now the rate for nitrogen is going to be 1/3 of the rate of hydrogen. It's going to depend on how much we have. And we can see this in our graphs. Our ammonia goes down, our nitrogen is going to go up, and our hydrogen is going to go up much faster than the nitrogen. So if we look at our values, we can see that as well. How the change here depends on how much of each of these we have in terms of their stoichiometric coefficients. So to clarify this and remove some of this dependence on how many moles we have, we're going to look at a different way of looking at our rates. So let's start out with what we know. We know that if we have this reaction, A is going to go down and B is going to go up. But when we talk about our rates, we don't care whether or not it goes up and down. We just want to have the change. So first of all, we're going to say our rates are always going to be written as positive values. For example, you don't go 60 miles an hour in one direction and minus 60 in the other. It's a rate, always positive. So to deal with this, we're going to take the change in concentration of a reactant, which here is A, and we're going to change the sign. Because A is going down, if we change the sign, it's going to become positive. So when we have an A going into B, we're always going to put a nice negative sign in front of our reactants to make our value positive. The B is already positive, so we don't change the sign. But this doesn't deal with the fact that we might have one of them or two of them. So what if instead we have 2A going into B? We know that the rate for A is going to be 2 times the rate for B, or the rate for A divided by 2 is going to be the rate of B. And we know that because it takes 2 A's to make 1 B. So the rate for A is going to be twice as fast. Now that 2 comes right here, and we are going to plug it into a fraction in front of our rate. So we're going to say that if we want to compare them, which is going to be relative rates here, if it's a reactant, it's going to be negative. To change the sign, we're going to take the stoichiometric coefficient and put it in the denominator, and then we're going to have the change of concentration over time. Because B is 1-to-1, its rate is going to be the change in its concentration over the change in time. If we have something complicated like this, we have AA plus BB goes into CC plus DD. For the reactants, these guys, we're going to put our negative sign. We're going to divide each of these by the stoichiometric coefficient. And for the products, because they're already positive, we simply only need to divide by the stoichiometric coefficients. If I want to find the rate for A compared to B, the rate of A is going to be, I'm just going to cross multiply, A over B times the change in concentration of B over the change in time. We can use our stoichiometric coefficients to relate our rates. So, a real life practice. We want to compare the rate of methane with the rate of oxygen. We know first of all, these guys are going to be reactants, so we have to put the negative sign in. We're going to take the 2 and put them down here. We're going to take the 2 for the water and put it right down there. And these are the relative rates between these reactions. And notice you can work backwards. If you wanted to go from our minus change in concentration of methane, delta T is equal to minus 1/2 the change in concentration of O2 delta T, and we wanted to turn this into a reactant because these guys are negative. We know they're reactants. And we know it's going to be however many we have down here is the number that we have in terms of our stoichiometric coefficients. It tells us that 1 methane reacts with 2 oxygens. If we continue to this, we're going to go to our products. Because there's no number down here in carbon dioxide, that's a 1 and 2 waters. We can go back and forth between the balanced reaction and the relative rate. So what influences the reaction rate? Well, first of all, concentration dependence. We're going to write a rate law. A rate law is a mathematical equation, which means we've got a rate and an equal sign, and the rate is going to depend on how much we have. So we're going to say that our rate is equal to some proportionality constant, which we're going to do a little lowercase k for, times the amount of reactants we have raised to some x power. When we want to ask or do this, we're just going to measure how fast, depending on how much. How fast, depending on how much, is our rate law. We are actually going to integrate it. We're going to pull a little calculus out, and we're going to integrate this rate law, and we're going to ask ourselves how long or how much is left. And then we're going to take and we're going to look at our temperature. Our temperature dependence says that this rate constant, K, our little proportionality constant from up here, is going to depend on the temperature. This is going to be exponential, and we're going to use this like the Clausius-Clapeyron, and we're going to be able to calculate rate constants as a function of time.